Hi everyone and welcome back to the channel. In today's video, we're going to be reviewing electricity and magnetism for the FE exam. This review is relevant for people taking the FE mechanical, electrical, or other disciplines exam. You can see in the upper right, I have the mechanical specification, where I've highlighted DC circuit analysis, which is going to be the focus of this video. In this video, we're going to discuss Kirchhoff's voltage law and current law. We're going to discuss mesh current analysis as well as source equivalence, which is Thevenin equivalent voltage and resistance. And we're going to reinforce those concepts by solving practice problems from my software, FE Interactive. You can see we have a few different circuits and our unknowns on the right-hand side, which are current flowing through specific resistors, as well as equivalent voltages and resistances. If you want to try out these free practice problems for yourself, you can do that using the first link in the description below. It'll take you to a screen just like this, where you can go ahead and click the filter button. Once you click filter, you can see that we solved a ton of practice problems here, and they're all free. You can click on electricity and magnetism and access the problems that we're going to solve today. All three of the problems that we're going to solve today. Let's get into the first problem. Okay, so you can see I have a calculator here. I'm not going to really be using it for this problem, but it will come in handy for problems 2 and 3. Now, the first thing that we have here is we're looking for the current flowing through that 18 ohm resistor in this DC circuit below. I'm seeing a few different sources, 22 volts and 15 volt voltage sources, as well as a bunch of different resistors. And our current of interest is flowing through this branch right here. This current here is what we're looking for. Okay, so what's super fundamental to analyzing DC circuits is the idea of Kirchhoff's voltage law, as well as Kirchhoff's current law, and lastly, Ohm's law. Ohm's law. Okay. Kirchhoff's voltage law says that the sum of the voltage rises plus the sum of the voltage drops inside of any loop inside of a circuit must be equal to 0. What about Kirchhoff's current law? It says that when you're analyzing any node, the current into that node must be equal to the current out of that node, where in and out have differing signs and their sum will be equal to 0. Lastly, we have Ohm's law, very classical. The voltage drop across a resistor is equal to the product of the current flowing through that resistor multiplied by the resistance of that resistor. Using these three fundamental laws, we're going to analyze the circuit. And really the easiest way to get what we're looking for to kind of isolate the current in that 18 ohm resistor is to perform a Kirchhoff's voltage law, analyzing this outer loop here. You can see that as we traverse that outer loop, we're only going to encounter the source here, and this 18 ohm resistor. So really there's only one unknown current that we're going to be finding here. So yeah, analyzing that outer loop is the best way to go about this. What's critical for using Kirchhoff's voltage law is really getting the signs correct. When you have sources, you want to start with those. When you're labeling the signs, the smaller of these two lines is the negative sign, and the upper one is the positive sign. The smaller of these two sources, that negative is associated with that, positive on the other side. And then as you're moving around in this loop clockwise, you experience a voltage drop due to a resistor. So you would be at a high voltage and then a low voltage traveling across that resistor, and that's because resistors absorb energy. Now that we have all our signs labeled for our relevant components of our outer loop, what we're going to do is write our first loop equation. Negative 22, and I started with that negative because as you travel clockwise, you're going to intersect that negative sign first. Keep traveling around the loop, we're going to encounter this positive 15, and these are both voltages. The last element that we're going to encounter here is a positive, and then the voltage drop associated with that 18 ohm resistor is going to be the product of 18, the resistance, times the current flowing through that resistor, which is I. Sum of the voltage drops inside of a closed loop must be equal to 0 by Kirchhoff's voltage law. We go ahead and solve for that current I. what we get is the difference between 22 and 15. That's 7. Move over the 18 and we get 7/18 of an amp, which is around 0.39 amps. If we go ahead and input that into our into FE Interactive here, 0.39 amps, we can check it. And if you don't have time to watch the full video solution, you can definitely try out these problems for yourself and view the typed solution right here, or if you prefer, the handwritten solution here. Let's go ahead and move into the second problem here. We're looking for the current flowing through that 4 ohm resistor. And this circuit here is a little bit more complicated. We're not sure about that current, but there are so many different unknown currents, and there's not a single loop that we can go around in order to just look for one unknown current. You see, if we chose this loop, for instance, we'd have a current that flows through here, and then that current would split at this junction, and it would split again right here. If we were analyzing this center loop here, again, we have a bunch of different junctions and a bunch of different currents that are running around. So the way we deal with this is by applying a specific technique, which is called mesh current analysis. And that really puts together Kirchhoff's voltage law and current law into a technique that we can use to get around situations like these. Now, it's possible to use Kirchhoff's voltage law and current law to solve a problem like this, but you'd end up with a bunch of equations, and mesh current really simplifies the approach. Standardizes it, right? All you do to apply mesh current is you label these loops, loop 1, loop 2, and loop 3. Once you have your 3 loops labeled, all you're going to do is apply Kirchhoff's voltage law and Ohm's law to the entire system. We're also going to go ahead and label these branch currents. What you see is the current flowing through that 10 ohm resistor. If we assume it's going to be a voltage drop, which is downward, high voltage, low voltage, what we're going to say is that is the difference between I1 and I2, the magnitude of the current in that branch. What about for this other 4 ohm resistor? Similarly, we can write that as the difference between I2 minus I3 if we assume the voltage drop is in this direction. High voltage, low voltage. Let's continue throughout the circuit and just label our pluses and minuses for the resistive elements. We'll have a voltage drop across this, a voltage drop across this, and I'm really looking at the loop direction to determine what the voltage drop is going to be here. I3 is going to be flowing from left to right, so we have a voltage drop there. And we can easily label the sign on our sources here. Minus for that little side of the source, plus for the bigger side. Same thing on the other side. Now that we have all our signs labeled, we're going to go ahead and apply mesh current, and we're going to end up with an equation that we are an equation for each one of these loops, 1, 2, and 3, that we get by applying Kirchhoff's voltage law to that loop. For the first loop, what I can see is that we have negative 105. We encounter that minus sign first, plus 7 multiplied by I1, plus 10 multiplied by the difference between I1 and I2. The sign is coming from intersecting that positive sign first, and the magnitude is coming from that labeled branch current that we saw by taking the difference between the 2 mesh currents, assuming that we have a downward current flow. What about for the second loop? For the second loop, we're going to encounter that minus sign first on the 10 ohm resistor, and the magnitude of current that is flowing through that resistor is equal to I1 minus I2 plus 13 times I2 plus 4 times the magnitude of the current is I2 minus I3 in that branch. And that must be equal to 0. Same thing as the top, that must be equal to 0 as well. In the third equation, we're going to similarly write that equation. Negative 4 times I2 minus I3. Negative is coming from encountering this minus sign first. And the magnitude of current in that branch is the difference between I2 and I3. Plus 6 times I3 plus 82. That's going to be equal to 0. So we have 3 equations here. we're going to clean this up, and what our real goal is to solve for this difference, I2 minus I3. So that's what we're going to be looking for here. Let's go ahead and simplify that equation to a form that we can plug into our calculator and solve for the different mesh currents. And then we're going to go ahead and solve this problem by taking the difference between the solve for I2 and I3. For the first equation, what that's going to reduce to is I'm going to compile all of the I1 terms. I'm seeing a 17 I1 above a minus 10 I2, and that's equal to 105. So that's our first equation. For our second equation, if I combine all the I1s, I have a negative 10 I1. And for I2, I'm seeing a positive 10 and 13. That makes 23. 23 plus 4 makes 27 I2. And what about for I3? I'm seeing a single term on that I3, a negative 4 I3. That must be equal to 0. Third equation, if we reduce it, I'm seeing a single I2 term. That's a negative 4 I2. And for I3, I'm seeing a 4 plus 6 term. That's a 10 I3. That's equal to negative 82. Now I'm going to show you guys how to plug this into the calculator here, the TI-36X Pro. Additionally, if you're looking for more calculator tips, because these definitely save you time on the FE exam, you can refer to this link video where I go through 13 relevant TI-36X Pro calculator tips. Okay, second system solve. We're going to go down to our 3x3 system and input the coefficients here. We have a 17 on that X term or the I1 term, a negative 10 on the I2 term, 0 on the I3 term, and a 105 on the right-hand side of that equation. Next equation, we have a negative 10, positive 27, negative 4, 0, 0 on that I1 term. Got to be careful there. Negative 4 on the I2 term, 10 on the I3 term is equal to negative 82. You got to watch out for that last equation, right? Remember that coefficient on the I1 is 0 there. We solve that. We have I1, I2, and I3. I really only care about I2 and I3 here. So I2 I have as 1.48 amps, and I3 is negative 7.6 amps. And if we take the difference I2 minus I3, which is the current flowing through that branch of interest, the 4 ohm resistor, the difference is, that's like 1.5 minus 7.6. And there's a negative sign, 1.5 minus a negative 7.6. That's equal to 9.1 amps. Let's go ahead and check that. 9.1 amps. We check it and we can view the explanation here. Okay, let's move on to the last problem now. In this problem, we're going to be really focused on how we perform these Thevenin equivalent voltage and resistance conversions of the circuit like this. Okay, so in order to find a Thevenin equivalent resistance, what you're going to want to do is short your voltage sources and open your current sources. And what that's going to do is, on the left-hand side, we essentially turn that 25 volts into a straight line. So that's shorting our voltage source. And what about for the current source? We're just going to open that current source, so we're getting rid of this branch here. What you can see is that we're going to end up with a 7 ohm resistor, which is in parallel with this 12 ohm resistor here. And those two sets of resistances are in series with this final 16 ohm resistor. That equivalent resistance that we calculate from this modified circuit is what we call the Thevenin equivalent resistance. Now, when you have two resistors in series, they sum. And when you have two resistors in parallel, calling these R1 and R2, the reciprocal of R1 plus R2 is 1 over R equivalent. And if we go ahead and invert both sides of this, what you could see is that R equivalent is just the inverse of that sum of reciprocals. So if we want to find the Thevenin equivalent resistance, all we do is 1/7 plus 1/12. We invert that and then add 16 since that's in series with them. We go ahead and solve for what that is. 1/7. Actually, it's faster to just do this on my calculator. It's pretty clear on how to do this. 1/7 plus 1/12. We can go ahead and invert that value. I'm seeing a value of around 4.42. Add 16 to that. 20.4 is approximately the answer. 20.4 ohms. Okay, that's great. We found the Thevenin equivalent resistance. Let's go ahead and go back to the original circuit to find the Thevenin equivalent voltage. All you have to do is find the voltage between those points A and B. So essentially, we are looking for this voltage right here, and that is what we call the Thevenin equivalent voltage. Now, if you have a circuit where A and B are not touching, then there's no reason for current to flow through that 16 ohm resistor because there's no potential difference between this point right here and this point right here. So we can essentially eliminate that 16 ohm resistor from our analysis. There's not going to be any current flow through that. So the Thevenin equivalent voltage is just the voltage across that 12 ohm resistor, which we can find by applying a technique like mesh current or Kirchhoff voltage and current law. I'm going to go ahead and use mesh current for this. Define my two loops here, loop number 1 and loop number 2. Now, when I go ahead and apply the equations here, the first equation, based off of loop 1, I see there is a current source. And when there's a current source, you can kind of pretty directly write down the equation associated with the first loop, for instance. That's just I1 minus I2, and that's assuming that we're going downwards. You can see that our current source is instead going upwards, so that's why it's equal to a negative 9 amps. This is our first equation. Our second equation, if we kind of analyze this overall loop here, which is kind of the combination between the first and second loop, we can label some of our signs, a plus and minus. And if we're going clockwise around this loop, what you can see is that we're going to have a voltage drop here across all these resistive elements, but the source sign is based off of the smaller side as a negative. We go ahead and write down the equation associated with that. We have 25 plus 7 times I1 plus 12 times I2 equals to 0, or 7I1 plus 12I2 is equal to negative 25. And that's our second equation. We're going to go ahead and plug this into the calculator here. Second, system solve. We have a 2x2 system, and essentially what we're looking for is I2. If we knew I2, which is this right here, then we could take the product of 12 and I2 by Ohm's law and find the voltage drop across the 12 ohm resistor, which is just the Thevenin equivalent voltage. Okay, let's plug in these two different equations. What we have is 1 minus 1 is equal to negative 9. What about for the second part? I have a 7 on that first part plus 12. That's equal to negative 25. We go ahead and solve that system. All we care about really is I2, which is the Y term. We see I2 is 2. If I2 is 2 here, we get a Thevenin voltage of the product of 12 times 2, that's 24 volts. So our final answer is 24 volts for V Thevenin and 20.4 ohms for R Thevenin. Let's go ahead and check that. Okay, and we did get the answer right. And you can see the written solution here. So if you're preparing for the FE mechanical exam and you enjoy these example problems, you're looking for more example problems like these, you can go ahead and try out my software, FE Interactive. It's the third link in the description below. you can get 2 months of subscription time for $10, so it's really affordable. Additionally, if you learned something from this video and you want to see more content like this, consider leaving a like and subscribing. Thank you for watching. I'll see you in the next video. Goodbye.